So I'm Dr. Lawlor, and this is the first lecture of CS441 Computer Architecture. So this is going to be sort of a strange lecture, which I think you'll notice in this semester is a recurring circumstance. And the strangeness is that I've been doing, so I'm teaching computer architecture, but I've been doing architecture. So you can hear that I'm actually here, and the location is this is my shop that I've been working on building most of the summer. So I think there are some really serious and interesting analogies between actual physical architecture and computer architecture. So I'm going to explore a couple of those during this lecture. So step one is to ask, well, how the heck do we build things? And in fact, the answer depends a lot on what you got. So, for example, if what you got is wood and you want to connect two pieces of wood together, well, if you're sort of in the third world or in the Alaska bush, you've got this sort of just unprocessed wood, right? There's random, unique shapes like we find out in the world. Here's a chunk of rope that floated down my creek, so I guess that's more or less totally natural. So if I want to join these two pieces of wood together, well, what do I got to do here? I gotta somehow tie these two pieces of wood together. Tying pieces of wood together is a skill, right? This is something that definitely takes some thought, some forethought, and some experience. Neither of which I've got here. So let's see. So if I tie these two pieces of wood together in some random way, so I'm not sure what the heck I'm supposed to be doing here. Boy, that works. I mean, the two pieces of wood are more or less connected, but depending on the skill here, I can get either good connection or bad connection. You know, it's the tying wood together, definitely an art, right? This is not a craft or a science. So you can actually standardize a lot of this stuff, and you can make your life a lot easier for assembling pieces of wood together by having standard materials. So, for example, here's dimension lumber. These are 2x4s. Dimension lumber is really nice because it's they're all uniform, right? 2x4s are more or less interchangeable. That means you don't have to actually pick out which piece you want. That means that you save lots of skill by having standardized parts, right? You've replaced the sort of human effort and ingenuity that it takes to figure out which piece of wood do I use where with total standardization. So the other amazing piece of technology we're using here is going to be a hammer. So the deal is a hammer and nails are a really beautiful piece of engineering. So the idea is, rather than having to figure out exactly how to tie these two things together with a chunk of rope or vine or what have you, well, you can just use you can use nails, and you can actually stick these things together. So I'll be darned. Let's see, if I put two nails into these 2x4s, you can get a better connection with less labor, right? And that's the standard thing that they're always going for in this sort of thing. And I'll be darned, nails actually hold these pieces of wood together pretty well. Hammering is also a skill. It's really easy to screw up and bend nails over if you've ever tried doing this, and it takes some time to actually install the nails properly. So this is not quite the totally automated machine design sort of modern approach to building you really want. So, for example, if one guy is trying to build an entire building, which is 60-some feet long and 30-some feet wide, then you really need to take it to the next level. So we need dimension lumber, we need nails, but we need some really efficient way to install the nails. So here's a pneumatic framing nailer. This is my Hitachi framing nailer, and it takes collated bricks of nails. And these are just a lot more efficient way to store your lots of nails, and of course it's powered by air power. So I can hook that thing up, and now the nice part about this is that I can install nails really quickly. It's not only is it substantially faster to install nails like that, it's a lot easier, right? So this is something that one guy can do, and one guy can actually can build a substantial building just using a pneumatic nailer and a whole lot of nails. By some count, I've installed like 30,000 some nails in this project so far, and I'm not done yet. So this is not just architecture, but computer architecture. So I claim that each of these steps that I've just described actually has an analogy in computing. So, for example, back in the day, computers were actually hand assembled. So, for example, this is Lisa, the Lawlor ISA card. So it's just a pluggable card. Now, the thing about Lisa is that I assembled Lisa by hand, right? So, over many an evening, I spent carefully, trimming these pieces of wire, sticking them in figuring out which slots they're supposed to go into, soldering it down. Many enjoyable hours doing that I never ever hope to repeat again in my life. So, I can build one ISA card like that. It took me, a week or something. It sure would stink if computers took a week to build each part, right? And there's one skilled person week is really expensive. So what you want is some way to automate this process, right? So you want to make it so that human beings are not having to actually manually figure out where each part goes and look at this piece of wire and say, this piece of wire is too short to connect these two pieces, so I'm gonna have to use some other piece of wire. And oh, how do I actually connect these pieces of how do I fit all these pieces of wire into the spot they're supposed to go into? This is definitely a skill, right? This is an art to try and build these things. So you can replace the art with some amount of automation. So here's the sort of automated version of that is a printed circuit board. So the nice part about a printed circuit board, and I had to refocus there. Printed circuit board actually has all of the wires are built in. They're actually are just a thin layer of copper on top of this board, and so you can see that there's copper in some places, and then this semi-transparent fiberglass in others. So here's a printed circuit board. It's got slots for all of the components, right? The stuff that is not just wires can just be soldered directly on the surface. The really beautiful part about a printed circuit board is that it's printed. So in this case, it really is a printed circuit board because I start these circuit boards out as a laser printout, and then that gets ironed onto the sheet of copper, and then I use acid to etch away the unironed pieces of the board. So so here, for example, I can make 6 of these at a time. And it really is possible, and it's not that horrible to actually crank out these boards, right? So I can make lots of identical printed circuit boards, which is really nice. So that when I finish one of them off here, for example, by soldering on the components, like here is a motor controller that's there for a little DC motor with a gear train. So the deal is you can solder on these components, which at the moment is a manual process for me, but I don't have to actually look at the wires and figure out the wires, etc. This is something sort of I've replaced a lot of the skill and effort with just automation, replicated parts, right? Standardized parts. So that means that I can actually make several of these things, and I can crank them out. The next step in automating these things is to automate not only the process of laying out wires on a board, but to automate the process of placing components on the board as well. So you can see here, for example, here's an actual commercial. This is just an Ethernet card, PCI Ethernet card, back when computers didn't all have PCI slots. So the idea is, you can see that there are a lot of components, right? A lot of things other than wires on this board. In fact, it's tough to see the wires because there's several layers thick of wires on this board. So this board costs I don't know, something like $5 now, and $5 does not buy a lot of skilled person time, right? That's only a few. So it only took an amortized a few minutes of skilled labor to actually make this board. So the idea is that this sort of recurring process, you can switch from lots and lots of manual labor. There's tying wood together with rope, lots of skill, lots of effort involved. As you have standardized parts, then you can actually eliminate a lot of that labor. And in fact, if you automate enough of this thing, so here there's a pick and place machine that sticks down the components here, you can replace essentially all of the labor to the point where cranking out these devices and doing the fabrication is essentially free. And because fabrication is free, you can actually put a lot more components on and still have the thing be affordable, right? So the complexity. So bottom line is that this is how we've actually scaled up the complexity of our computers, right? This is why computers of today are a lot more advanced than computers of yesteryear, and it's because we've gotten better at actually building them. In other words, the assembly, the architecture has gotten more machine friendly, more standardized, less human labor, less human effort and skill, and what we've replaced that with is standardization and machine parts.